Now we're going to look at systems of linear equations. So we're going to have 2 or 3 different equations, and our goal is really to look to see if there's some kind of intersection there. So we're going to focus on lines in 2 dimensions, which means we're going to have 2 variables in this section, and then we're going to talk about what happens if we have 3 variables in the next section. So every system of linear equations will have one of the following. There's either going to be one solution, which means they're going to cross at one intersection point. There's going to be no solution, which means that all the equations do not cross. Or there could be an infinite number of solutions. So let's look at the possibilities if we have 2 equations and we have 2 variables. If there's an intersection, then there's going to be one solution. So that first picture shows you what could happen here. We have 2 equations, the red equation and the blue equation, and they cross at this point. That's the solution point. All of these are going to be written in terms of an x-coordinate and a y-coordinate. So we say that that system is consistent and that the equations are independent of each other. Now, if the lines happen to be parallel, then that means there's not going to be any solutions. So there's no solutions here. And the reason there's no solution, and you can see it in that second graph, is because there's no intersection point for 2 lines that are parallel with different y-intercepts. So they're never going to cross anywhere. If there's no solution, then we say this is an inconsistent system. The third case is if the lines lie on top of one another. And these are called coincident lines. And what's happening there is that one line is actually a multiple of another one. So let's say we had something like x plus y is equal to 2. And then we had 2x plus 2y is equal to 4. So you can see how these are the same line. If we were to multiply this one by 2, then we would end up with that second one. So it seems like almost a silly incident there. But what's going on is that those lines are on top of each other. And that means that every point that is on this line is actually on this line. So in this case, we have an infinite number of solutions. So we say this is a system that is consistent, but the equations are dependent. So then when this happens, we usually write these in terms of like a variable t. And we'll talk about that in a little bit. Now, anything we can do in 2 dimensions, we can do in 3 dimensions. So there's lots of different ways this could happen in 3 dimensions. And you can see some of the different ways this could happen here. These are actually all the ways that we could happen. So I want to start with that first one. In 3 dimensions, we're not really dealing with lines necessarily. We're dealing with planes. So when we write something in terms of x, y, z, we're talking about 3 planes. So we could have 3 planes that are parallel, in which case there's not an intersection point. We could have 2 lanes that are parallel, but a third one cuts through. Still not a single intersection point. Or we could just have 3 planes that intersect in some way, but there's not one single intersection point. Or we could have 2 parallel planes that are coincidental, which means that one's a multiple of the other one, and then we have a third one that's parallel to those. In all 4 of those cases, there would be no solution because there's not a common intersection between all 3 of the planes. Now, if there's one solution, then what's going to happen is all 3 of those planes are going to intersect at one particular point. And we would write that in terms of an ordered triple. It would have an x-coordinate, a y-coordinate, and a z-coordinate. Now, there are a couple of ways or 3 ways actually, that we could have an infinite number of solutions. We could have 2 planes that intersect, and the third one intersects also. And you can see where that intersection would be. It would be right here. So this would be an intersection on a line. that last one is also going to intersect on a line. We have two planes that are coincidental, which means that one is a multiple of the other one. And then you have that other plane that's intersecting, and those all intersect right here, which is going to be on a line. And then this scenario, we have an infinite number of solutions, but what's going on here is that we have three planes that are coincidental, which means that each one is a multiple of the other ones. So there is an infinite number of solutions in that case also. But in this case, it's not a line of intersection, it's actually a whole plane of intersection. So how do we solve a system of equations? In this section, we're going to focus on substitution and elimination. Now, we could also graph these and we could find the intersection point. But I want to focus on substitution and elimination here. And we're going to do substitution on a few of these, and then we're going to do elimination on a few of these. So let's start with substitution. In substitution, your goal is to solve one equation for a variable. And then you're going to sub that into the second equation. And then that's going to give you an equation that you will be able to solve. And then we can back substitute. We are always looking at ordered pairs if we have two equations and two variables. So let's look at this one. I'm going to call this guy equation 1 and this guy's equation 2. So I'm going to solve equation 1 for one of those variables. Now it doesn't matter which one we pick. Ideally what you want to do is solve for the easiest variable you can. In this case, any of these variables in either equation would be easy to solve for. So I'm just going to solve that first one for y. So to solve this for y, we would have to move x to the other side. So we're going to have y equals negative x plus 8. So this is just a rewrite of that first equation. So our next step is to substitute this into equation 2. Equation 2 says x minus y is equal to 4. And we're going to substitute in negative x plus 8. That's an x. So let's simplify this. We're going to distribute that negative. Okay, I want you to notice at this point we have an equation that just has one variable in it, which means we could solve this. Let's solve for x. We have 2x, and I'm going to go ahead and move that 8 to the other side. And then let's divide by 2. So we're going to get x is equal to 6. Okay, now we do need an ordered pair. So let's substitute this back in for y. So now our goal is to find y. So we know y is equal to negative x plus 8. I'm going to use that guy because we've already solved that for y. So if we substitute in, x is negative 6. So y is equal to 2. So our ordered pair has an x coordinate of 6 and a y coordinate of 2. Alright, that's using the substitution technique. Now I want to look at number 25 in the same kind of way. So in 25, we have 2x plus y is equal to 1. I'm going to call that equation 1. And the second one I'm going to call equation 2. So, lots of different options here. Here's what I see. It's going to be really easy to solve that first equation for y. So I'm going to go for it. I'm going to solve equation 1 for y. So to do that, I need to move that 2x to the other side. And we can do that by subtracting 2x. And now we're going to make a substitution. This is going to go into equation 2. It's going to always go into the second equation. So when we sub in, we have 4x plus 2y is equal to 3. If we substitute in for that y value, we're subbing in negative 2x plus 1. So now notice we have an equation that just has x's in it. Check out what's going to happen here. Do you see how those cancel? So we get 2 is equal to 3. Now, is 2 equal to 3? And the answer is no, that's not equal to 3. So anytime we're solving an equation and we get some kind of untrue statement, that tells us there's going to be no solution to this. So we do not have a solution for that guy. Now, you're probably asking, well, why don't we have a solution? Well, it's going to turn out these are going to be parallel. So let's look at this. If we were to take that first equation and solve it for y, which is what we did above, we got y equals negative 2x plus 1. So we can see that that slope is a negative 2. Let's look at that second equation and let's solve it for y. We can move that 4x over. And then we could divide everything by 2. So we see that the slope is also negative 2. So they're not the same line. The y-intercepts are different, but the slope is the same. So these are parallel lines. Okay, they're not the same line, but they're not coincidental lines, but they are parallel lines. So then what that means for us is that there's not going to be a place that these are going to intersect. And since there's no intersection point, then there has to be no solution to that system of equations. Now let's look at 23. And I'm going to use elimination to solve this one and to solve 30, so you can see what's going on there. So if there's something, a variable that's easy to solve for, substitution would be a good technique to use. In this case, if I try to solve for x or to solve for y in either equation, I'm going to get fractions. You know, you can certainly do substitution with fractions, that's fine. But a better option might be to do elimination on those. And with elimination, what you want to do is you want to eliminate one of the variables. And we're going to do that by adding these equations together. Now, if I were to add these equations together right now, nothing's going to cancel out. No. So what we're going to have to do is we're going to have to multiply each of these equations by something. And we can choose to eliminate either x or y. So I'm going to choose to eliminate y. So to eliminate y, I need these numbers to be the same so that when I add the equations together, I'm going to get a 0y. So let's multiply each of these equations by something. As long as you do the same thing to both sides of the equation, it's going to be a legal move in math. Now, we can multiply by any number, but we cannot multiply by 0. And that's just because if we multiply by 0, then everything goes away, because 0 times anything is 0. So ideally, I want these two numbers to be the same but opposite signs. So that least common multiple between a -6 and a 4 would be a 12. Let's multiply this top one by 2 and this bottom one by 3. So when we do that, look at what happens to this. Now the top equation is 6x minus 12y is equal to 4. The bottom equation is 15x plus 12y is equal to 3. So now you can see that if we were to add those two equations together, -12y plus 12y is 0y. So it's eliminating that variable. So we have 21x here. That's going to be equal to 7. Divide both sides. So x is equal to 7 over 21, and that reduces to 1/3. Now, we still have to find y. We can substitute that 1/3 into either equation. We're going to get the same answer for y regardless. So I'm going to substitute that into the first one. So I'm going to label this guy 1 and this guy 2. So if I substitute into the first one, it's 3x. That x is 1/3. Minus 6y is equal to 2. So if we multiply, 3 times 1/3 is 1. We can subtract 1 from both sides. Divide by -6. So we're going to get y equals -1/6. So our solution point is 1/3 -1/6. So with elimination, your goal is to eliminate a variable. Sometimes you have to multiply both equations by something. Sometimes you don't have to multiply by anything. Let's go back to that first one we did, number 17. We had the system x plus y is equal to 8. X minus y is equal to 4. So in this case, this is really set up so we could eliminate y pretty easily. Okay, all we have to do is add those two equations together because we already have the same number in front of y where one's positive and one's negative. So if we add those two equations together, we're going to have a 0y, which would just be 0. So we have 2x is equal to 12 divided by 2, and we're going to get 6 for x. So I'm going to sub this into the first equation. 6 plus y is equal to 8, which means y is equal to 2. So then our answer would be the 0.62. So what this is telling us in this case is that if we were to graph these two equations, they would intersect at the 0.62. We could use substitution or elimination on any of these problems. This one was nice. It substituted easily. It's also easy to do elimination with. I want to do one more. Let's look at 30. We have the system 3x minus y is equal to 7. And 9x minus 3y is equal to 21. Let's use elimination on this. So if we look at this one, adding the two equations together right now would not eliminate a variable. Let's choose to eliminate x here. We need to multiply at least one equation by something. Let's multiply that top one by -3. And if we do that, I'm going to write it down here. We're going to have -9x plus 3y is equal to -21. And then we have 9x minus 3y is equal to positive 21. So this is that first equation multiplied by a -3. This is that second equation. Now this one's really interesting. Check out what happens. If we were to add these two equations together, we're going to get 0 is equal to 0. Anytime we get a true statement like this in math, that means that there's going to be all real numbers, infinite number of solutions here. So this is a consistent system. It's also a dependent system. If we were to analyze this a little bit further, notice that that equation and that equation look the same. If we were to multiply that top one by a positive 3, then we would get that second one. So this is that case we were talking about here, where those lines are lining up perfectly, and that's forcing us to have an infinite number of solutions. So now we need to talk about how to write those solutions. What would that solution set look like? So when we write that final solution, we're just going to take one of those equations and we're going to solve it for y. So if I were to solve this equation for y, I can move the 3x over, and then I can divide everything by -1. So we're going to get y equals positive 3x minus 7. So then that solution itself is going to be a line, but we need to say what x can be. And in this case, x can be all real numbers. So a more concise way to write that solution set, we could say y is equal to 3x minus 7. This gives us the form of what those y values would look like. And x can be any real number, so we can write it this way. This is mathematical notation for that. This funny looking e means element of, and then that r means all real numbers. So that says that x can be any real number, but y has to be in this form. So there's our final answer for that one.